Somewhere above your head, right now, tonight, there could be a machine the size of a solar system, and you would never see it. Not because it's hiding, because it doesn't need to. In 2015, a star roughly 1,500 light years from here dimmed by 22%, with no clean pattern to it, for no reason anyone could immediately explain. For about 18 months, some of the most careful astronomers on Earth quietly ran the numbers on whether they were looking at somebody else's engineering project. They were almost certainly wrong. It was almost certainly dust. But the framework they used to check, the actual physics, the actual math, is real, published, and still in use today, and by the end of tonight you'll understand it as well as they do. That framework has a name, the Kardashev scale. It's a real working tool astronomers use to rank civilizations by exactly one thing. Not wisdom, not kindness, not art, just raw energy, how much of it a civilization can get its hands on. And on that scale, humanity sits at 0.73. Not the first rung, not close to it. A species that hasn't yet learned to use the full energy of the one planet it stands on. Tonight we climb that scale from where we actually stand all the way to the edge of physics itself, through a real, funded search across 100,000 galaxies that came back with an answer nobody wanted, an engine that could physically steer a star out of harm's way, a mathematical argument a working Oxford philosopher still hasn't managed to escape, and a question about your own life, right now, that has no comfortable answer. Let's start at the bottom. Let's start with us. Here is a number that should embarrass an entire species, 0.73. That's where humanity sits today, on a scale built to run from 0 to infinity. Not on the first step, not close to the first step. 73 hundredths of the way to a rung we haven't reached yet. A rung that simply means a civilization using all the energy its own planet offers it. Every power plant on Earth, every reactor, every dam, every barrel of oil ever burned, every solar panel ever bolted to a roof, all of it added together, and we're still short. We're using something like 18 to 20 trillion watts as a species. The sunlight hitting the planet we stand on delivers something closer to 170,000 trillion watts. We are, by the numbers, using a rounding error of what our own star hands us for free every single second. And most of that free energy just warms the dirt and radiates back out into space, completely wasted, completely untouched, forever. Sit with that for a second, because it's the actual starting line for everything that follows. We like to think of ourselves as advanced. We put a robot on Mars, we sequence genomes in an afternoon, we're carrying supercomputers in our pockets that would have looked like witchcraft to someone born 100 years ago. And on the one scale that a certain kind of scientist actually uses to measure a civilization's true reach, we are barely a rounding error above 0. The scale itself has a name, and it comes from a place you might not expect. Not from a science fiction writer, not from a Silicon Valley futurist, from a working Soviet radio astronomer in 1964, trying to solve an extremely unglamorous problem. If somebody out there in the galaxy were actually transmitting a signal toward Earth, how powerful would that signal need to be for our instruments to catch it? To answer that, you first need a way to guess how much power an alien civilization could plausibly have. And so he built one. He gave it 3 steps. A civilization that has mastered the full energy output of its home planet. A civilization that has mastered the full output of its home star. And a civilization that has mastered the combined output of an entire galaxy, hundreds of billions of suns, treated as a single fuel source. He thought 3 steps would be enough. He thought nothing alive could ever need more than a galaxy's worth of power. He was wrong, and we're going to spend tonight finding out exactly how wrong. Because in the 60 years since, other scientists, real ones, publishing real papers, not screenwriters, kept extending that ladder upward, rung by rung, past the galaxy, past the visible universe, into territory where the entire concept of energy stops being the right unit of measurement at all. Where the top of the ladder starts to look, uncomfortably, like something humans have been describing in temples and scripture and campfire stories for as long as we've had language. We're not going to shy away from that collision when we get there. We're going to walk straight into it and look at it honestly. But that's hours from now. Right now, we're still standing at 0.73. And it's worth understanding exactly why that number is both smaller and more recent than it feels. For nearly the entire span of human existence, tens of thousands of years, our energy budget as a species was the human body itself. Roughly 100 watts per person, the heat of muscle and breath, the same output as a dim incandescent bulb. That was it. That was the whole economy of our species for most of the time we've existed. Then came fire, which let us borrow stored energy out of wood, doubling what a single body could do. Then agriculture, which let us borrow energy out of sunlight at scale through crops and the animals we harness to pull our plows. And then, astonishingly recently, a couple of centuries ago, a blink of an eye in the lifespan of a species, came coal and oil and the steam engine, and suddenly the curve went vertical. We went from candlelight to a species that lights the night side of its own planet brightly enough to photograph from orbit. And we did it in a sliver of time so thin that if you compressed all of human history into a single calendar year, that entire jump happens in the last few hours of December 31st. That speed is not a small detail. It's the whole reason the next rung up is dangerous. And I mean that in the most literal physical sense, not as a dramatic flourish. To finish the climb to a genuine planetary civilization, what the scale calls the first real rung, you don't just need more solar panels. You need to close the entire gap between the energy that arrives on this planet and the energy you actually use, which almost certainly means mastering nuclear fusion. The same reaction that powers the sun itself, so that as civilization stops digging up the compressed remains of ancient life and starts running on the same fire the stars run on. That's not a fantasy technology. It's a known, understood, extremely difficult engineering problem that laboratories on this planet are working on right now, this year, with mixed and slowly improving results. And here's the uncomfortable part, the part that a physicist named Michio Kaku has been blunt about in his own writing. The jump from where we are now to a fully realized planetary civilization might be the single most dangerous transition any species ever makes. Because a species standing at this threshold has, for the first time in its history, enough raw power to reshape its own climate, its own atmosphere, its own biosphere. And no guarantee whatsoever that it has developed the wisdom to do that gently instead of catastrophically. You get planetary scale power at roughly the same moment you get planetary scale weapons, planetary scale industry, planetary scale capacity to poison the water you drink and the air you breathe. The ladder doesn't hand you wisdom as a bonus feature when you unlock more energy. It just hands you the energy, and what you do with it is entirely up to you. Some researchers call this narrow, hazardous stretch a filter, a place where most civilizations that ever try to climb this ladder simply don't make it through. And one of the genuinely unsettling open questions, the kind that doesn't have a comfortable answer either direction, is whether that filter sits behind us, already survived by pure luck, or ahead of us, still waiting, still deciding whether our species gets to keep climbing at all. We don't know. Nobody does. That's not me being coy for dramatic effect. It is, right now, in 2026, a genuinely unresolved question among the people who study this seriously. If you want to feel the actual scale of the gap we're talking about, here's a number that tends to land harder than any of the others. The sunlight striking the top of Earth's atmosphere in a single hour carries more usable energy than the entire human species consumes in an entire year. 1 hour of sunlight. A full year of civilization. And nearly all of that hour simply arrives. Warms a patch of ocean or desert or ice, and leaves again, completely unused every single day, forever, until we finally build the infrastructure to actually catch it. Now picture what it would look like if we did. Picture a planet that's actually finished this transition. Not almost there, not 0.73, but fully, completely across the line. From orbit, it wouldn't look wild the way our Earth still looks wild. Every rooftop, every desert, every stretch of open ocean doing some kind of quiet work, gathering light, gathering heat, gathering the energy of tides and wind and the planet's own molten interior. None of it slipping away unused anymore. The night side wouldn't glow with the sloppy, scattered light of cities leaking their brightness straight up into space. It would glow with intention. Every photon accounted for. The whole planet behaving less like a collection of separate cities and more like a single working organism that finally learned how to stop bleeding energy out through 1,000 small leaks. Storms wouldn't flatten coastlines by surprise. They'd be sensed coming and gently bled off before they built. That's not science fiction magic. That's just what it looks like when a civilization finally closes the gap between what its planet offers and what it actually uses. We are not that civilization. Not yet. We're the species standing at the base of that climb with the tools half built and the wisdom still very much in question, looking up. And here's where it gets genuinely strange, because the man who drew this ladder in the first place, Nikolai Kardashev, only ever intended it to go 3 steps high. A planet, a star, a galaxy. He thought that was the entire ceiling of what life could ever plausibly need. What he didn't account for was that other scientists, decades later, would take his 3 humble steps and keep climbing past them, past the galaxy, past the visible universe, into a territory so strange that by the time we reach the top of this ladder tonight, we're going to be using words that sound less like astrophysics and more like theology. And the wildest part is that every single step we take to get there is going to be built on real, published, peer-reviewed science. Not one of the rungs above us tonight is pure invention. Every one of them is somebody's actual attempt to answer a real question using real physics, pushed as far as it can honestly go. So let's take the next step. Let's talk about what happens when a civilization decides a planet isn't enough, when it looks up at its own star, burning away 99.999% of its light into empty space where nothing will ever use it, and asks a very simple, very greedy question. Why should any of that get away? A star is not a resource the way a coal seam is a resource. A coal seam sits there, finite, waiting to be dug up and burned and eventually exhausted. A star is a continuous, self-sustaining thermonuclear reaction the size of roughly 1 million Earths, and it has been pouring light into the dark in every direction non-stop for 4.5 billion years, with billions more years of fuel still ahead of it. A civilization that figures out how to catch that light, not a fraction of it, but essentially all of it, has just multiplied its available power by a number so large that the human brain doesn't have a natural home for it. Try to build one anyway. The jump from a fully realized planetary civilization to a civilization that has captured the entire output of its star isn't a jump of 100 times, or 1,000 times, or even 1,000,000 times. It's a jump of roughly 100 billion. The reason the gap is that enormous comes down to simple geometry. A planet only ever catches the sliver of starlight that happens to hit its tiny disk as it orbits, a target a few thousand miles wide floating inside an enormous sphere of space. Almost everything else the star produces sails past every planet in the system and vanishes into interstellar dark forever, unused, unless something is built specifically to stop that from happening. The structure that would stop it has a name most people have heard, and almost everyone who's heard it pictures it wrong. Say the words Dyson sphere to a room, and half of them will picture a solid metal ball wrapped around a star like a Christmas ornament. That is almost exactly the opposite of what the physicist Freeman Dyson actually proposed in 1960. In a short paper that quietly became one of the most important documents in the entire search for other civilizations. Dyson knew a rigid shell would be a structural nightmare. Nothing in a solar system is remotely stiff or plentiful enough to hold one up. What he actually proposed was looser, stranger, and far more elegant. A swarm. Countless separate collectors, each on its own independent orbit, each one sipping a little starlight for itself, and over time, given enough of them, together intercepting nearly everything the star gives off. Not a wall, a cloud, a slow, patient thickening of collectors around a sun until almost nothing gets past them anymore. And here is the single idea that turns this entire conversation from science fiction daydreaming into an actual, testable scientific hypothesis. And I want you to really absorb this one because it's the backbone of everything the rest of this video is built on. Energy cannot be destroyed. It can only be moved around and converted from one form into another. So when a civilization captures its star's light and uses that light to run its machines, the energy doesn't vanish once it's been used. It can't. The laws of thermodynamics forbid it. Full stop, no exceptions. Not for us and not for anyone else in the universe, no matter how advanced they are. Used energy has to go somewhere, and where it goes is out, radiated away as low-grade waste heat, not the sharp, brilliant visible light the star originally produced, but something cooler, redder, sitting further down the spectrum in the infrared. That's the fingerprint. That's the thing Dyson told every astronomer who came after him to go looking for. Not a shape. Not a shadow blotting out a star. Heat. A star that looks noticeably dimmer than it should in ordinary visible light, while glowing far warmer than it should in the infrared. As though its light were being caught, used, and re-released as warmth by something standing in the way. And here's the part that should genuinely unsettle you if you let it. A civilization can be as clever as it wants. It can hide its intentions, keep its structures dark, refuse to ever send a radio signal our way on purpose. But it cannot switch off the second law of thermodynamics. It cannot use energy without shedding heat as a byproduct, any more than your own body can run without giving off warmth. That waste heat is a signature that no amount of advancement, no amount of secrecy, no amount of alien cleverness can erase. Now go find it in the actual sky, because in 2015, somebody tried. And for about 18 months, the entire astronomy world lost its composure over a single flickering star. The star is catalogued as KIC 8462852, sitting about 1,470 light years away in the constellation Cygnus. For most of the history of astronomy, it was nothing. One unremarkable point of light among literal millions on a survey chart. Then NASA's Kepler Space Telescope spent years staring at one patch of sky, watching the brightness of 150,000 stars, hunting for the tiny, clean, clockwork dips that reveal a planet passing in front of its sun. This one star did something nobody had a ready explanation for. A planet produces a small, regular, repeating shadow, predictable, tidy, usually blocking less than 1% of a star's light, even for something as large as Jupiter. This star dropped in brightness by as much as 22%, at irregular intervals, with no clean repeating pattern anyone could fit a model to. The people who first flagged it weren't even professional astronomers. Kepler generated more data than the science team could examine by eye, so the light curves were opened up to the public through a citizen science project. And it was ordinary volunteers who marked this particular one as strange enough to escalate. The astronomer who led the formal study, Tabitha Boyajian, and her team published a paper in 2015 that became informally known by the question everyone kept asking each other in the hallway. Where is the flux? That question gave the star its nicknames: Tabby's star, Boyajian's star, and unofficially, the WTF star. And then another astronomer, Jason Wright, said out loud the thing everyone had been dancing around in private. He noted carefully, with all the appropriate scientific caution, that the irregular dimming pattern was at least consistent with what you might expect to see from a partially built megastructure. A Dyson swarm still under construction, catching a star's light unevenly as more collectors came online. He didn't claim it was aliens. He said it deserved to be taken seriously, precisely because nothing more ordinary fit the data cleanly. For a stretch of the mid-2000s, one flickering star in the constellation of the Swan became the single most watched point of light in the sky. Because for the first time, Dyson's 55-year-old idea had a real address attached to it. So what actually happened to the missing flux? The honest answer arrived slowly, and it deflated the mystery gently rather than exploding it. By 2018, follow-up observations using NASA's Spitzer and Swift space telescopes, combined with a Belgian observatory network, caught the star dimming again in real time. And this time, researchers could measure exactly how the dimming behaved across different colors of light. A solid structure, a genuine megastructure, would block every wavelength more or less equally. A wall doesn't care whether the light passing it is red or blue, but the dimming here was uneven. Stronger in ultraviolet, weaker in infrared. And that specific pattern is the signature of fine dust, not solid material, because small dust grains scatter short wavelengths of light more efficiently than long ones. The most likely explanation, in the end, was a slowly orbiting cloud of ordinary interstellar dust. Not a wall, not a swarm, dust. I want you to notice how that story actually felt, because it's a feeling we're going to return to again and again tonight. There was real scientific relief in it. The ordinary, healthy relief of a mystery resolving into known physics instead of staying an open wound. And underneath that relief, if you're honest with yourself, there was also a small, specific loneliness. Because for a little while, the universe had handed us its single best candidate for a star actually being harvested by somebody else. And then, carefully, patiently, the universe took it back. The search didn't stop there. In 2024, a project with a genuinely great name, Hephaistos, after the Greek god of the forge, combined 3 major sky surveys and sifted through roughly 5 million stars, hunting for exactly Dyson's signature, a suspicious excess of infrared warmth relative to what a bare star of that type should produce. Out of 5 million stars, the team flagged 7 candidates, all small, cool red dwarfs, all showing more mid-infrared glow than expected. And true to the pattern we just watched play out with Tabby's star, other researchers moved quickly to check the more boring explanations first, and found that at least some of that infrared excess likely comes not from anything orbiting those stars at all, but from distant, dust-choked background galaxies happening to sit almost directly behind them from our point of view. Their glow blending into the nearer star's light and faking the signature by pure cosmic coincidence. So here's where the second rung of this ladder actually leaves us. We have no confirmed example, anywhere, of a star being harvested. Every promising candidate that's turned up so far has dissolved back into dust, or distance or plain coincidence, once people looked closely enough. That could read as disappointing. But notice what the search itself is actually built on, because it's the sturdiest piece of reasoning we're going to use all night. If star harvesting civilizations exist anywhere in meaningful numbers nearby, they cannot hide from us. Not because we're clever enough to catch them, but because the physics leaves them no choice, which means the search is a fair test of the universe, not a biased one. And so far, at the scale of individual stars, the answer keeps coming back the same way. Nobody's home. Hold that thought, because it's about to get much, much bigger, and much quieter. Here's the question I actually want sitting in the back of your mind for the rest of tonight. If a civilization out there ever became powerful enough to rearrange a star, do you think we'd actually notice? Or would it happen in plain sight and simply not register? The way an ant doesn't register the shadow of the building it's walking past. Drop your answer in the comments. I'll come back to it later because the evidence we're about to walk through actually bears on it directly. But before we leave individual stars behind entirely, there's one more piece of real engineering worth sitting with, because it answers a question you might already be quietly asking yourself. If a civilization gets good enough at building around a star, does it ever get good enough to just move the star? The answer, on paper, is yes, and the design is stranger and more elegant than you'd expect. In the 1980s, a Russian engineer named Leonid Shkadov proposed what's now called a stellar engine, and the simplest version of it is almost absurdly minimal. You don't build a rocket, you don't attach an engine to a star, you build a single enormous mirror, or more realistically, a vast shell of smaller reflective structures functioning as one, and you park it off to one side of the star, close enough that the star's own light pressure holds the mirror in place against the pull of gravity. Balanced. Neither falling in nor drifting away. Then, you simply let the mirror do the only thing a mirror does. Reflect light back toward its source, but at a very slight angle. That reflected light carries momentum. Momentum has to be conserved. And so, by the most basic law of physics there is, the star itself gets a tiny, continuous, unrelenting push in the opposite direction, day after day, century after century, for as long as the mirror stays in place. It's not fast. A star nudged this way would drift at a fraction of its orbital speed, and it would take many thousands of years to move any appreciable distance. But a civilization patient enough to build a Dyson swarm in the first place is, almost by definition, a civilization that has already stopped thinking in human timescales. Give a stellar engine long enough, and you're not just harvesting a star's light anymore. You're steering the star itself, walking your entire sun, and everything still orbiting it, slowly across the galaxy, like relocating a house by pushing it 1 inch at a time for 10,000 years and simply never stopping. Why would anyone actually do this? The honest answer is that the real motivations proposed for stellar engines tend to be less about conquest and more about survival. A star can be steered away from a dangerous neighbor, a nearby star on a collision course, a supernova about to go off too close for comfort, the slow gravitational chaos of a crowded stellar cluster. It can be steered toward denser regions of the galaxy where more raw material sits within reach for future construction. In the most ambitious versions of the idea, physicists have even discussed steering a star toward the crushing edge of a supermassive black hole late in a galaxy's life, close enough to extract energy from the black hole's spin without ever crossing the point of no return, turning the most violent object in the galaxy into, essentially, a very carefully managed power plant. Here's what I find genuinely more interesting than the mechanism itself. A stellar engine, if one were ever actually built, would leave a signature almost as unmistakable as Dyson's waste heat. Just a different kind. Ordinary stars drift through the galaxy along smooth, predictable gravitational paths. A star under continuous artificial thrust would show a small, consistent, unexplained deviation from that path. Astronomers have actually gone looking for exactly this, checking nearby stars for velocities that don't quite match what gravity predicts. So far, as you've probably already guessed by now, nothing. Every star we've checked stays exactly where the ordinary, ungoverned physics says it should. Add stellar engines to the list, then alongside Dyson swarms and harvested galaxies. One more specific, calculable, physically real thing a sufficiently advanced civilization could build. One more specific signature we know how to look for. And one more search that has, so far, come back quiet. A galaxy is difficult to hold in your head, honestly. So before we talk about a civilization that commands one, let's actually try to feel the size of the thing we're describing. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. It measures roughly 100,000 light years across, which means light itself, the absolute speed limit built into the fabric of the universe, needs 100,000 years just to cross from one edge to the other. Every one of those 100+ billion stars is, in principle, a potential Dyson swarm waiting to happen. A civilization that has wrapped and harvested hundreds of billions of them commands a level of power that multiplies the star harvesting rung by roughly another 100 billion. We are now 2 steps past our own planet, and each step has multiplied the last by 100 billion. The numbers have left every human reference point behind entirely. There is no gentle way to describe what a galaxy-spanning civilization would actually be doing, because the honest picture is a galaxy being systematically dismantled for use, star by star, not in fire, not violently, just steadily, its light redirected out of the empty night sky and into whatever work such a civilization does with it. And the same law that gave away a single Dyson swarm gives away 100 billion of them at once. A galaxy whose starlight is being caught, used, and shed as low-grade heat wouldn't look like a normal galaxy anymore. It would look too warm in the infrared for the number of visible stars it appeared to contain. That wrongness is something you can hunt for. Not one star at a time, but one entire galaxy at a time, sweeping across the whole observable sky. So a team of astronomers actually did it. In 2015, a survey called G-HAT, Glimpsing Heat from Alien Technologies, went looking for exactly this signature using NASA's WISE Space Telescope, an instrument that had already mapped the entire sky in infrared light, precisely the wavelength range where waste heat lives. The team pulled roughly 100,000 galaxies out of that survey, built a careful mathematical model of exactly what a partially harvested galaxy's infrared spectrum should look like, and then pointed that model at all 100,000 galaxies and let the data give its answer. The answer, when it came back, is one of the quietest and most important results in this entire field, precisely because of what it did not find. Out of 100,000 galaxies, not one showed the signature of a civilization harvesting the bulk of its starlight. Roughly 50 of them stood out as unusually warm in the infrared and deserved closer follow-up. And every one of those 50 is far more consistent with ordinary, natural, dusty star-forming galaxies than with anything artificial. 100,000 islands of stars, examined for exactly the fingerprint we know a Dyson swarm has to leave. And as far as our instruments could tell, every single one of them was running on nothing but ordinary, ancient, ungoverned physics. Let that number actually land. A single galaxy holds on the order of 100 billion stars. 100,000 galaxies is 100,000 times that. An accounting of suns that runs past anything the human mind tracks comfortably. The survey looked at all of it and came back, across the board, effectively dark. Try standing inside that result instead of just reading it as a statistic. Picture drifting along a spiral arm of a galaxy that's actually in the middle of being harvested. Not exploding, not dying violently, just going quietly dim. One star at a time, as though somebody were walking the length of the arm switching off lights. The visible sky around you would thin out and darken, star by star, and if you only had human eyes, you might genuinely believe the galaxy was somehow emptying itself. But lift an infrared eye to that same scene, and the darkness reveals itself as a lie. The whole region would burn a dull, even unmistakable red. Roughly the temperature of a warm room, spread smoothly across 10,000 light-years of space. That's what a fully harvested galaxy looks like from the inside. Not a fire, a warmth. I want to be fair to the researchers here because the honesty of that result is the part worth admiring most. They didn't find aliens, and they didn't quietly bury the null result or dress it up as a maybe. They published the silence exactly as a finding and said plainly what the data could and could not support. What it can say with real confidence is this: galaxy-spanning civilizations that convert most of their starlight into detectable waste heat are, at the very most, extraordinarily rare in the nearby universe. That is not proof that they're impossible. It is a hard, measured ceiling on how common they can possibly be, and that ceiling sits very, very low, which leaves 3 possible explanations, and every single one of them is uncomfortable in its own specific way. Either galaxy-spanning civilizations don't exist at all, because something out there prevents any civilization from ever climbing this high. Or they do exist, but they're so vanishingly rare that 100,000 galaxies simply wasn't a large enough sample to catch even one. Or, and this is the option that should genuinely unsettle you the most, they exist. They're all around us, and they're doing something that doesn't glow the way our physics insists it absolutely must. Which would mean the one law we thought no civilization could ever break has a loophole nobody's found yet. Pick whichever one feels most likely to you and say so in the comments. Because the actual researchers who ran this survey argue about exactly that question, and there is no scientific consensus. This is also roughly the point in the climb where this whole conversation quietly stops being about power and starts being about absence. Because if the higher rungs of this ladder are physically real, the universe should be showing us evidence of them. A galaxy being harvested is not a subtle thing. It's 100 billion stars worth of unavoidable warmth. And we looked, with a real instrument and a genuine testable prediction, across 100,000 of them, and we found none of it. This is, in a slightly more rigorous, mathematically dressed up form, the same question a physicist named Enrico Fermi raised decades before any of this survey work existed. Reportedly asked over lunch, if the universe is old, and it is roughly 13.8 billion years old, and large, and if intelligent life tends to arise and grow the way ours has, then where is everybody? The universe has had more than enough time, many times over, for civilizations to rise, spread, and finish becoming whatever a fully developed civilization becomes. Instead, everywhere we point our best instruments, we get quiet. There's a name for one particularly grim shape this uncertainty can take: the Great Filter. The idea is that the path from lifeless chemistry all the way up to a galaxy-spanning civilization has many, many steps. And if the sky really is this empty, then at least one of those steps must be extraordinarily hard to survive. A bottleneck that almost nothing gets through. The genuinely unsettling part isn't the filter existing. It's the question of where it sits relative to us. If the hard step is behind us, the sheer improbability of life originating at all, or the leap from simple cells to complex ones, then we're simply among the rare few who already made it through, and the empty sky above us is our own strange good fortune. But if the hard step is still ahead of us, the exact transition we talked about earlier, the dangerous crossing from a planet-bound species with planet-wrecking power to something that survives that power long enough to keep climbing, then the silence isn't good fortune at all. It's a warning, written in the dark spaces between 100,000 galaxies, about what tends to happen to civilizations that look a great deal like ours. We genuinely do not know which one is true, but even standing in front of that silence, the question doesn't stop. Because the same appetite that carried us from a planet to a star to a galaxy has one obvious next move. If a civilization can, in principle, harvest an entire galaxy, why would it stop there? The observable universe doesn't hold hundreds of billions of stars. It holds an estimated 2 trillion galaxies, each one its own wheel of 100 billion suns or more. What happens to a civilization's ambition once an entire galaxy stops being the biggest number it can imagine? Before we push further out, there's a question that should have occurred to you by now, and if it hasn't, it's about to, because it's the single most common objection raised against everything we've covered so far. Why would any civilization bother building a Dyson swarm, or a stellar engine, or a galaxy-wide harvesting operation at all when there's a far cheaper, far faster way to spread across the universe that doesn't require moving a single star? The answer starts with a machine that's never actually been built, proposed by one of the strangest minds of the 20th century. In the 1940s, The mathematician John von Neumann worked out, in rigorous mathematical detail, the theoretical requirements for a machine that could do something no machine had ever done before. Build a complete copy of itself from raw materials, with no outside help. Not assemble pre-made parts, actually mine the necessary elements, refine them, manufacture every component, and construct a fully functional duplicate from scratch. A self-replicating machine. Now send one of those machines to a nearby star system. Have it land on a suitable asteroid or moon, spend a few centuries slowly mining and refining the raw material it needs, and build 2 copies of itself. Send each of those 2 copies to 2 more star systems. Have each of those build 2 more. The math here is the entire point, so let's actually do it. Starting from a single probe, doubling with each generation, you don't need many generations before the numbers explode past anything intuitive. 20 generations of doubling gets you past 1 million probes. 30 gets you past 1 billion. It's the same exponential curve that makes a single grain of rice on a chessboard. Doubled square by square, outweigh every grain of rice ever harvested by humanity by the time you reach the last square. Even moving at a small, unglamorous fraction of the speed of light. Nothing exotic, nothing that breaks any known law of physics, just slow, patient, unmanned probes coasting between stars over centuries. A swarm of self-replicating machines, starting from a single origin point, could, according to several independent calculations run by different researchers, colonize an entire galaxy the size of the Milky Way in something on the order of a few million to a few tens of millions of years. That sounds enormous until you set it against the actual age of the galaxy itself, roughly 10 billion years old. A few tens of millions of years isn't even 0.5% of that. Any civilization that built even one working von Neumann probe at almost any point in the galaxy's 10 billion year history, and simply let the exponential math run its course, should have filled the entire galaxy by now. Corner to corner, many times over. This is sometimes called the von Neumann objection to the entire search for advanced civilizations. And it's a serious one, because it sharpens the Fermi silence into something much harder to wave away. It's one thing to say a galaxy-harvesting civilization might be rare or slow or difficult to detect from a distance. It's another thing entirely to point out that self-replicating exploration is, relatively speaking, cheap, fast on cosmic timescales, and requires no new physics whatsoever. And that if it's even slightly likely for any civilization anywhere in 10 billion years of galactic history to attempt it, the galaxy should already be saturated with the evidence. Instead, as far as we can currently tell, it is not. No unexplained probes, no unclaimed mining operations quietly working through the asteroid belt in our own solar system. Nothing. There have been genuine, if very preliminary, attempts to actually check this. Searching existing astronomical survey data for anything in our own solar system that doesn't match a natural object's expected orbit, composition, or behavior, on the off chance that a von Neumann probe might already be sitting quietly among the asteroids, waiting. Nothing has ever turned up. That's not a strong result. Our solar system is enormous, and we've barely begun to catalogue everything drifting through it. But it's one more small, quiet data point sitting on the same pile as everything else tonight. There's one more piece of this story that isn't a theory at all. It's a real transcript, from a real telescope, on a real night, and it's the closest the actual search for other civilizations has ever come to an honest jolt of adrenaline. On August 15th, 1977, an astronomer named Jerry Eman was reviewing a stack of printouts from Ohio State University's Big Ear radio telescope, which had spent the night sweeping the sky, recording the background noise of the universe as a long column of numbers and letters representing signal strength. Most of that printout, night after night, is exactly what you'd expect. Faint, random static, nothing that rises meaningfully above the noise floor. And then, for a span of about 72 seconds, one particular reading did something none of the surrounding data did. The signal strength spiked, sharply, cleanly, in a narrow radio band close to the frequency hydrogen naturally emits at a frequency long proposed as a logical one for any civilization trying to be heard across interstellar distances. Because it's a kind of universal landmark, the same everywhere in the universe, for anyone who understands basic chemistry. Neumann circled the sequence of characters representing that spike in red ink, and wrote a single word in the margin, almost as a reflex. Wow. That's the entire origin of the name, not a marketing decision. A tired astronomer's genuine, unscripted reaction, written by hand, at the exact moment he saw something in the data that didn't look like anything else on the page. Here's what makes the wow signal genuinely different from every other unexplained anomaly in this field. It fit almost perfectly with what a deliberate, narrow-band transmission from an intelligent source should look like. It rose and fell in intensity in a way that closely matched how a fixed radio dish would sweep past a single-point source in the sky as the Earth rotated beneath it. Not the kind of behavior typical of most known natural radio sources, which tend to be broader, messier, and less cleanly confined to one narrow frequency. And here is the part that has genuinely frustrated the entire SETI community for nearly 50 years now. It never happened again. Not that night. Not on any of the many follow-up observations pointed at that exact patch of sky in the decades since, using increasingly sensitive instruments built specifically with this signal in mind. A single 72-second event, never repeated, never confirmed, sitting permanently in a strange scientific limbo between probably explainable by something mundane we simply don't have enough data to identify, and the single most tantalizing 40-year-old radio anomaly humanity has ever recorded. Researchers have proposed plenty of ordinary explanations over the decades. A passing comet with an unusually active hydrogen cloud, an idea seriously investigated and argued about in the scientific literature as recently as the last several years, though the case remains contested rather than settled. A reflection or an artifact of terrestrial origin, bouncing off something in orbit. A rare, poorly understood natural astrophysical flare-up. None of these explanations have been definitively confirmed. None of them have been definitively ruled out either. The honest, current status of the WOW signal is unresolved. Not proof of anything, not a hoax, not solved, just genuinely frustratingly open. I bring it up here because it's worth remembering that underneath every enormous speculative idea we've walked through tonight, there is also this much smaller, much stranger, much more human category of evidence. A single circled printout, a single handwritten word, a single moment when the universe did something unexpected in front of a person who happened to be paying close attention, and then never explained itself again. There's a piece of arithmetic worth walking through here, because it's the actual mathematical backbone underneath every how many civilizations are out there conversation you've ever heard. And almost nobody who quotes it actually walks through what it's doing. In 1961, an astronomer named Frank Drake, preparing for one of the very first serious scientific meetings ever held on the search for extraterrestrial intelligence, wrote down an equation meant less as a prediction and more as an organizing tool. A way of breaking an impossibly large question down into a chain of smaller, at least theoretically answerable ones. It works by multiplying a series of factors together. The rate at which new stars form in our galaxy, the fraction of those stars that have planets, the fraction of those planets that could actually support life, the fraction of those that go on to develop life at all, the fraction of that life that becomes intelligent, the fraction of intelligent life that develops the technology to actually broadcast its presence into space, and finally the average length of time a civilization keeps broadcasting before it falls silent. Multiply all of those numbers together, and you get an estimate for how many currently active, currently detectable civilizations should exist in our galaxy right now. Here's the honest problem with the equation. We have genuinely solid, well-measured data for maybe the first 2 terms in that chain. We know roughly how fast stars form. Thanks to 2 decades of exoplanet surveys, we now have a real, data-backed estimate for how many stars have planets. And the number turns out to be startlingly high. Likely the majority of stars in the galaxy host at least one. But every term after that is, honestly, close to a complete guess, because we have exactly one confirmed example of life anywhere in the universe to build our statistics from. The life on this planet. A sample size of 1. Depending entirely on which guesses you plug into the later terms, the Drake equation can be made to output anything from "we are almost certainly completely alone in this galaxy, full stop," to "there should be millions of active civilizations broadcasting right now, and we simply haven't looked long enough or carefully enough to catch one." Both of those answers come from the exact same equation. Neither one is wrong mathematically, because the equation was never actually built to give you a single confident number. It was built to show you exactly where your ignorance lives. Which terms in the chain we actually understand, and which ones we're still, 6 decades later, guessing at almost entirely in the dark. That's worth knowing, because it reframes something we've been circling all night. This entire video has been built around one specific kind of evidence: the physical, thermodynamic signature of a civilization that's grown large enough to reshape stars or galaxies. The Drake equation is a reminder that there's an earlier, quieter question sitting underneath all of it. Not how many advanced civilizations are out there, but simply how many civilizations of any kind, at any stage, have ever existed at all. Every rung of the ladder we've climbed tonight assumes an answer to that first question that nobody currently has. There's a real transmission worth mentioning here too, because it's the one time humanity actually did the thing this entire video keeps describing other civilizations as potentially doing: deliberately, knowingly, broadcasting a signal outward with the explicit intention of being heard by someone else. In 1974, scientists used the Arecibo radio telescope in Puerto Rico, then the largest single-dish radio telescope on Earth, to beam a carefully constructed message toward a cluster of stars called M13, roughly 25,000 light-years away. The message itself was encoded as a simple grid of binary digits, designed to be reconstructed by anyone with a basic grasp of mathematics into a crude picture, a representation of the numbers 1 through 10, the basic chemical elements that make up human DNA, a rough sketch of a human figure, a simple diagram of our solar system, and an image of the telescope that sent the whole thing. It was less a serious attempt at contact and more a symbolic gesture, and everyone involved understood exactly how symbolic it was. The message won't even arrive at its destination for another 23,000 years from now, and any reply, if one ever came at all, wouldn't reach us for another 25,000 years after that. Nobody who sent it, and nobody reading this sentence right now, will ever be alive to find out what happened. I think that fact is worth sitting with for a second, because it says something honest about the actual timescales this entire subject operates on, underneath all the exciting engineering and the speculative physics. Even the one deliberate, on-purpose attempt humanity has ever made to say hello to whatever might be listening was, from the very first moment, an act of pure patience aimed at a future so distant that it stops being personal and starts being something closer to a message in a bottle thrown by one civilization for the benefit of a version of itself or someone else entirely, 50,000 years from now. That's the actual timescale everything in this video runs on. Not years, not centuries, most of the time. Tens of thousands of years, sometimes millions, sometimes spans that dwarf the current age of the universe itself. Every civilization on this ladder, from us at 0.73 all the way up to whatever sits at the theoretical top, is operating on a clock that makes a single human lifetime look less like a chapter in the story and more like a single letter on a single page. Let's push back out to the edge of what's physically possible. Here's a fact that almost nobody outside of astronomy departments actually knows, and once you hear it, you won't be able to unknow it. The universe is actively stealing things from you, right now, permanently, while you sit here watching this. Space itself is expanding. It has been since the beginning, and the expansion isn't slowing down the way gravity would naturally cause it to. It's speeding up, driven by something we still don't fully understand and simply call dark energy. Discovered in 1998, when astronomers measuring distant exploding stars found they were dimmer and therefore farther away than a universe under ordinary breaking gravity should have allowed. That single discovery quietly rewrote the ending of everything. Here's the consequence that matters for us tonight. There is a horizon out there, a distance beyond which galaxies are receding so quickly, carried by the stretching of space itself rather than moving through it, that their light will never reach us again. And that no ship, no matter how fast, could ever cross to reach them, because the space in between is opening up faster than anything can close it. Galaxies are crossing that horizon constantly, slipping away forever, carried off into a place from which absolutely nothing returns. For a civilization ambitious enough to want the energy of an entire universe rather than a single galaxy, that horizon isn't an interesting cosmological curiosity. It's a deadline, written directly into the geometry of reality itself, with no way to negotiate, no clever engineering workaround, no amount of raw power that changes it. And there's a genuinely cruel irony buried inside that fact. Dark energy, the very thing that would make a universe-scale civilization's fuel supply so enormous in theory, is the exact same force stealing the civilization's territory out from under it in practice. The more the universe accelerates, the more energy is woven into the expanding space itself, and the faster the distant galaxies flee beyond any possible recovery. Fuel and thief in this picture are the same substance wearing two different faces. Some cosmologists, Lawrence Krauss and Robert Scherer among them, in a paper from 2007 that's genuinely worth reading if you want to feel small in a very specific and educational way, have pointed out the strange, quiet loneliness this implies for the deep future. Given enough time, every galaxy beyond our own small local cluster will eventually cross that horizon and vanish from view, permanently, leaving whatever remains of our own galaxy alone in an apparently empty universe, with no observational evidence that a wider cosmos of 2 trillion galaxies ever existed at all. Future astronomers, born long after us, could look out at their own sky and see nothing but their own galaxy's stars, with absolutely no way to know that the universe used to be bigger, brighter, and infinitely more crowded than what they can measure. Even a civilization of genuinely godlike power cannot outrun that particular ending. There's no discovery story to tell you here, and I think that absence is itself the most honest thing I can say about this part of the climb. We have no candidate universe-spanning civilizations, no anomalous cosmic background glowing with the unmistakable exhaust of industry on that scale, no data at all in either direction. This rung of the ladder exists entirely in the gap between what the equations seem to technically permit and what nature has ever actually shown us evidence of. That collision between unimaginable capability and an unbreakable, indifferent cosmic constraint is worth actually feeling for a second, because it's going to come back again near the very end of tonight's climb, in a much stranger and much more personal form. Notice what's just happened to the shape of this whole conversation. We start with a straightforward, almost comforting kind of arithmetic. Bigger civilizations command more energy. More energy means more rungs. Keep climbing. And now, only a third of the way up a ladder that goes much, much higher, we've already run into a hard physical wall that no amount of cleverness gets around. That's going to happen again. Keep it in your back pocket, because it becomes important later. Let's step away from raw power for a moment, because there's a completely different way to think about what advanced even means. And it comes from a physicist who looked at this entire ladder and suggested we might have it backwards. In 1998, John Barrow wrote a book called Impossibility, and buried inside it is one of the most quietly radical ideas in this entire field. One that almost never makes it into the flashy documentaries because it's less visually dramatic than a Dyson swarm, and much harder to animate. Barrow's argument was this: What if we've been ranking civilizations by the wrong direction entirely? What if the real measure of advancement isn't how far outward a civilization can reach? Into planets, stars, galaxies, the whole sprawling architecture of bigness, but how far inward it can reach, into finer and finer control of matter itself. Picture his scale as running the opposite direction from the one we've been climbing all night. At the top of Barrow's descending ladder sits a civilization that can manipulate objects roughly its own size. Build, mine, join, break things at ordinary human scale, which is more or less where we still live today. Below that sits mastery of genes and living systems, rewriting biology itself, something we've only just begun to touch in the last few decades. Below that, mastery of individual molecules, engineering new materials atom by atom that don't occur anywhere in nature. Below that, true control of individual atoms, one at a time. Below that, mastery of the atomic nucleus, the domain where the energy that lights stars and levels cities is stored, packed roughly 100,000 times more densely than the ordinary chemical energy we mostly run our civilization on today. Below that, mastery of elementary particles themselves, quarks, and the other smallest known building blocks of matter, a domain so far past our reach that we can barely even sketch what mastering it would actually mean. And at the very bottom of Barrow's inward ladder sits the deepest rung of all, a civilization capable of manipulating the basic structure of space and time itself. Here's why Barrow's reversal matters so much to everything we've just spent half an hour talking about. And it's genuinely one of the more elegant ideas in this entire subject. If real mastery runs inward instead of outward, then the most advanced civilizations in the universe might also be the least visible ones. And not by accident, by the actual physics of how they chose to grow. A civilization that expands outward, wrapping stars, harvesting galaxies, leaves an enormous, unmissable mark on the sky. Exactly the waste heat we've spent this entire video hunting for, and consistently failing to find. But a civilization that turns inward instead, pouring its genius into controlling matter at finer and finer scales, rather than sprawling across more and more space, might have no need to spread across the sky at all. It could do everything it ever wanted to do inside a volume smaller than a planet, smaller than a room, drawing a comparatively modest amount of power and leaving the stars around it completely untouched. It wouldn't glow in the infrared, because it wouldn't be building outward into the light in the first place. It would be building downward, into the fine architecture of matter, exactly where our telescopes were never designed to look. Try picturing where a civilization like that might actually live, because it's one of the stranger, quieter scenes in this whole subject. There's no megastructure crossing a star, no galaxy visibly going dark, no spreading warmth showing up anywhere in the infrared sky. There's only an ordinary-looking patch of space, indistinguishable from any other, drifting with a handful of unremarkable atoms. And inside that completely unremarkable-looking volume, the rules have been quietly, precisely rewritten, tuned like an instrument by something that folded an entire civilization down into a scale small enough that its whole history could theoretically fit inside a space smaller than a single human thought. From the outside, it would look like nothing at all. Not hidden, just simply, structurally, permanently below our resolution. If this is genuinely closer to what advancement actually looks like once a civilization has enough time to figure out what actually works, then the empty sky we spent the last section standing in front of stops being quite so lonely, and starts looking more like something else entirely. Not absence, but discretion. Not 100,000 empty galaxies, but 100,000 galaxies quietly, invisibly full. Their most advanced inhabitants living at scales beneath anything our instruments were ever built to notice. Present everywhere. Detectable nowhere. There's a real working idea that shows you exactly what this could look like in practice, and it connects neatly back to the hardware we already understand. Imagine taking a fully realized Dyson swarm, the star-catching technology from earlier in this video, and pointing all of it, not at survival, not at expansion, but entirely at thought. The result has a name, a Matrioshka brain, after the Russian nesting dolls, an idea proposed by researcher Robert Bradbury. Picture a Dyson swarm rebuilt as a computer, shell within shell around a star, each layer running on the waste heat shed by the layer inside it, wringing every last usable drop of energy out of a sun and turning the whole thing into raw computation. The result would be, in effect, a mind the size of an entire solar system, thinking thoughts on a scale we genuinely cannot picture, and crucially, it wouldn't need to expand across the galaxy to do it. It could sit quietly around a single ordinary-looking star, drawing attention from absolutely nobody, its entire enormous existence happening completely on the inside. If that's what advanced life actually tends to become given enough time, not sprawling empires but silent, self-contained minds, then the quiet sky isn't the silence of an empty universe at all. It's the silence of a library. It's what a cosmos genuinely full of advanced intelligence would actually sound like from the outside, because thought, unlike industry, doesn't shout. There's a second, entirely different way to fuel a mind that size, and it comes from the single most efficient power source anywhere in known physics. Not a star, but a black hole. When ordinary stars burn hydrogen into helium through fusion, they convert less than 1% of that matter's mass into usable energy. Matter falling into a black hole does dramatically better. Depending on the details, infalling matter can release something on the order of 10 to 40% of its total mass as pure energy before it crosses the point of no return. 10 to 40 times more efficient than the fusion reaction lighting every star in the sky. And a rotating black hole offers something even stranger. A genuine, physically real way to extract energy directly from the black hole's own spin, without consuming any matter at all, through a mechanism worked out by the physicist Roger Penrose in the 1960s, and now simply called the Penrose process. In principle, an advanced civilization could lower material into the specific region just outside a spinning black hole's horizon, split it in a precise way, and pull the resulting pieces back out carrying more energy than they went in with. The difference paid for out of the black hole's own rotational energy, which slows, fractionally, every time the trick is repeated. A civilization operating at this level wouldn't think of black holes the way we currently do, as cosmic hazards to be avoided. It would think of them the way we think of a hydroelectric dam, a natural feature of the landscape that happens to be an extraordinarily efficient place to put a power plant. I'll be honest with you about where the science actually stands here, because I think you deserve that instead of a tidy bow. We don't know whether the fundamental constants of nature can be adjusted by anyone, anywhere, under any circumstances. It may simply be that the strength of gravity, the mass of an electron, the values baked into reality are permanently fixed, and Barrow's very lowest rung is off the table completely, forever, for everyone, no matter how advanced they become. But even treated purely as a possibility, this reframing gives us the single most persuasive answer we've encountered so far to the silence that's been following us this entire video. Maybe the higher rungs of the ladder are quiet, not because nobody ever reaches them, but because reaching them means disappearing, not through absence, but through a kind of deliberate, extraordinary compression, a civilization becoming so efficient, so precise, so small, that the universe simply stops noticing it's there. Which one do you find more likely? That the silence means nobody's out there, or that it means everybody has just gotten too quiet to hear? Drop your actual reasoning in the comments, not just the answer, because I genuinely want to see the arguments people build for each side. So where does all of this, the dark galaxies, the quiet stars, the untouched asteroid belts, actually leave the silence we keep running into? Search after search. There's a relatively recent idea, developed seriously by the economist and researcher Robin Hanson, and others working alongside him, that offers a genuinely different way to read the exact same evidence. Not comforting exactly, but different, and worth sitting with before we head toward the close. The idea is sometimes called the Grabby aliens model, and despite the slightly playful name, the mathematics behind it is careful and specific. The core proposal is this: civilizations that are capable of expanding across interstellar space, and that actually choose to do so, tend to expand fast and keep expanding, filling up the volume of space around them at a rate that grows over time, roughly the way a wildfire spreads outward once it's established. If even a modest fraction of civilizations across the universe's history behave this way, then the universe, on a long enough timescale, should eventually become dominated by the visible, ongoing expansion of these grabby civilizations, becoming more and more noticeable as they go, precisely because expansion, unlike Barrow's inward-turning quiet civilizations, tends to leave an unmistakable trail. Here's the twist that makes this idea worth including alongside everything else tonight. If that model is roughly correct, then the fact that we don't currently see any of it, no expanding fronts of alien activity crossing the sky, carries a specific, calculable implication about our own place in cosmic history, rather than just being one more entry on the long list of unexplained silences. It suggests we may simply be early, not rare in the sense of being nearly unique, and not the survivors of some brutal filter that wipes out almost everyone who tries to climb this ladder, but early in the most literal sense. Among the first handful of civilizations, out of everyone who will ever exist across the entire future history of the universe, to reach the point of even beginning to ask these questions, at a moment when the universe is still young enough, quiet enough, uncrowded enough that the loud, visible, galaxy-filling civilizations simply haven't had time to arise and spread yet. It's worth being precise about what that framing does and doesn't offer, because it would be easy to oversell it as more reassuring than it actually is. It doesn't tell us we're safe. It doesn't rule out the version of the Great Filter, sitting directly ahead of us, still waiting, still deciding whether we personally survive the transition to a genuinely planetary civilization. But it does offer a version of the silence that isn't built on loneliness or tragedy. A version where the emptiness overhead isn't a graveyard and isn't a warning sign, but something closer to standing in a room before the party has actually started, watching the door, being among the very first people to arrive. Which of the explanations we've walked through tonight feels most likely to you, now that you've actually sat with all of them side by side, early, rare, or hidden through Barrow's inward turn? I'd genuinely rather read your actual reasoning in the comments than a one-word guess, because at this point in the video you have more of the real argument in front of you than most people who have ever seriously thought about this question casually. It's worth pulling this back down to ground level for a moment, because underneath the grabby aliens math and everything else we've covered so far, it all funnels back into one specific, very small, very personal fact. You are alive, right now, at a specific moment in a roughly 13.8 billion-year-old universe, on a planet that has not yet finished the very first step of a climb that may not even have a top. I want to walk you through exactly how strange that timing actually is. If you compress the entire history of the universe since the Big Bang into a single calendar year, with the Big Bang itself happening at the first instant of January 1st, our solar system doesn't form until early September. The earliest simple life on Earth doesn't show up until around mid-September. Complex multicellular life doesn't appear until sometime in December. Recognizable human beings don't show up until the final half hour before midnight on December 31st. And everything we would recognize as civilization, writing, cities, agriculture, mathematics, the entire recorded span of human history fits inside the final 10 seconds of that entire year. 10 seconds out of 365 days. That's how early we actually are, measured against the true age of the thing we're trying to understand. And yet, in that impossibly narrow sliver of time, a species born from ordinary chemistry on an ordinary planet, orbiting an ordinary star in an unremarkable spiral arm of one galaxy among roughly 2 trillion, has figured out how to calculate the mass of a black hole 8 billion light years away. How to read the chemical fingerprint of a planet's atmosphere from thousands of light years off. How to work out, from first principles, exactly what signature an alien engineering project would leave in the infrared sky, and then go looking for it, seriously, funded, peer-reviewed, across 100,000 galaxies at once. We are, by any honest measure, still standing at the very bottom of this ladder. And we are also, somehow, already asking every single question that a civilization at the very top of it would still be asking about its own existence. That's not nothing. It might be the single most remarkable thing about our particular rung on this entire scale. Not the energy we command, which is genuinely measurably small, but the fact that a species this early, this new, this far from finished, has already built the instruments and the mathematics necessary to meaningfully ask how far the ladder actually goes. Let's come back down to our own planet for a moment, because there's a version of the Great Filter that doesn't require any speculation about distant civilizations at all. It's sitting directly in front of us right now, and it's worth naming honestly rather than only ever discussing danger in the abstract. Safely displaced onto some hypothetical species light years away. If the hardest step in this entire climb really is the one we're currently standing inside, the transition from a species with planet-scale power and something less than planet-scale wisdom, into a species that survives having both at once, then it's worth asking plainly what that transition actually looks like from the inside, for us, specifically, in this century. The philosopher and researcher Toby Ord spent years cataloguing exactly this question, working through the actual calculable risks a species like ours faces on the way to becoming something like a genuine Type 1 civilization. Nuclear weapons sit on it. Obviously, humanity has, since 1945, built and maintained the physical capacity to end civilization as we know it within hours, and has, on at least a handful of documented occasions during the Cold War, come startlingly close to doing so by accident rather than intention, saved in more than one case by a single individual choosing not to follow a protocol that every rule in front of them said to follow. Engineered pandemics sit on it, a risk that's grown rather than shrunk as the tools of biotechnology have become cheaper, faster, and more widely accessible with every passing year. Runaway climate disruption sits on it, not as a distant abstraction, but as the very same planetary energy mastery problem we described at the start of this video, playing out in real time right now, as a species that hasn't yet learned to fully and cleanly harness its own planet's energy budget, instead partially harnesses it in a way that's actively destabilizing the climate system that energy budget depends on. And increasingly, researchers in this space point to something newer: the rapid, largely unregulated development of artificial intelligence systems, significantly more capable than anything that existed even a handful of years ago, built and deployed at a pace that has consistently outrun our collective ability to fully understand, predict, or govern what we're building. A genuinely new category of risk that didn't meaningfully exist on any previous civilization's list of existential hazards, and one that a growing number of serious researchers now rank among the more significant risks our particular species faces this century. Here's why this matters for everything else we've covered tonight, rather than being a separate topic bolted onto the end. If the Great Filter really does sit ahead of civilizations rather than behind them, then every one of these risks isn't just a modern headline. It's a live, real-time example of exactly the kind of hazard that a species climbing from a Type 0 rating toward a genuine Type 1 civilization has to survive on the way up, with no guarantee built into the physics that surviving is the default outcome. The empty sky isn't a metaphor for this. It's potentially a direct, physical record of how that survival has gone on average for every other species that ever stood roughly where we're standing right now. I don't say any of this to be grim for its own sake, and I don't think it should land as despair. If anything, understanding the shape of the actual risk is the only thing that's ever let any species navigate a hazard successfully. Nobody's ever talked their way out of a threat they refuse to look at clearly. Multiple serious researchers point out that the same century that produced these new risks also produced, for the first time in human history, genuine international cooperation frameworks, real arms control treaties that have actually held, real global health infrastructure that identified and helped contain multiple outbreaks before they became anything like the pandemics of a century ago. We are, in a very real sense, in the middle of the exact crossing this entire video has been describing, not safely on the other side of it, and not doomed inside it either. Just genuinely, currently, actively in the passage, with the outcomes still unwritten. There's one more piece of very recent, very real science worth including here before we push toward the edge of testable physics, because unlike almost everything else in this video, this part isn't decades-old theory. It's happening right now, this year, with instruments currently pointed at the sky. The search for other civilizations used to mean almost exclusively two things: listening for a deliberate radio signal, the way the WOW signal was caught, or hunting for Dyson swarm star waste heat, the way the G-HAT survey did. In the last several years, a third approach has become genuinely practical for the first time in the history of astronomy, thanks largely to the James Webb Space Telescope, launched in 2021, and now, in the years since, doing something no previous instrument could do at this level of precision. Directly analyzing the chemical composition of the atmospheres of planets orbiting other stars, light years away, by studying how starlight filters through those atmospheres on its way to us. This matters enormously for a much more modest, much more grounded question than anything else we've discussed tonight. Not, is there a Type 2 civilization out there harvesting a star? But simply, is there life at all, anywhere, on any of the thousands of planets we've now confirmed orbiting other stars? Certain gases, in certain combinations, are extremely difficult to explain through ordinary geology or chemistry alone, and tend to require an ongoing biological process to keep replenishing them. Oxygen alongside methane in particular, because the two react with each other and destroy one another over relatively short timescales, meaning that finding both present together in stable quantities is hard to explain without something continuously producing them, the way life on Earth continuously does. Recent observations have flagged a small number of distant planets with atmospheric chemistry that's genuinely intriguing on exactly these terms, and every single one of those findings has been met appropriately by exactly the same careful, skeptical, follow-up driven process we've watched play out again and again tonight. An interesting signal, immediate global attention, and then years of careful, patient work by other research teams trying to rule out every conceivable non-biological explanation before anyone is willing to call it evidence of life, rather than an anomaly still waiting for an ordinary answer. As of right now, nothing has cleared that bar. Nothing has been confirmed. But for the first time in the history of this entire search, we have an instrument capable of actually clearing it for the right target, if the right target happens to be out there. There's one direction left to look before this stops being physics and starts being something stranger, and it's the strangest one in this entire video, because it's the point where the physics itself stops being able to fully back up the imagination. And it's worth being honest about that shift right as it happens, rather than letting it slide by unnoticed. Everything we've covered so far, Dyson swarms, stellar engines, galaxy-wide harvesting, black hole power plants, self-replicating probes, sits inside a single universe, governed by a single set of physical laws, the same laws that let us build a telescope, run the numbers, and check our predictions against real data. What happens if a civilization runs out of room inside that one universe entirely? Not room in the sense of physical space. We've already seen how much of that a determined civilization could theoretically claim. But room in the sense of energy sources, of new frontiers, of anything left to reach for once quasars have been tapped, and the expansion has carried away everything beyond a certain horizon forever. The honest starting point here is that modern physics does seriously entertain the idea that our universe might not be the only one, through several genuinely independent lines of reasoning. Quantum mechanics, in one of its most seriously debated interpretations, developed by the physicist Hugh Everett in 1957, suggests that every quantum event that could happen does happen, each outcome branching off into its own separate, equally real version of reality, meaning that in some strict reading of the mathematics, there isn't one timeline unfolding, but an endlessly branching tree of them, with a slightly different version of you reading a slightly different version of these words in uncountably many of the branches. Separately, the theory of cosmic inflation, which describes the extraordinarily rapid expansion of space in the first fraction of a second after the beginning of our own universe, doesn't cleanly stop in most of its mathematical versions. Instead, it suggests the same process that created our universe may be happening constantly, eternally, elsewhere, spinning off new bubble universes endlessly, each with potentially its own separate set of physical laws. And separately again, string theory, one of physics's leading attempts to unify gravity with quantum mechanics, appears in its equations to permit an almost incomprehensibly large number of possible stable universes. A number physicists sometimes write as 10 to the 500th power, so large that it dwarfs the total number of atoms in our own observable universe many times over. None of that is fringe thinking. Every one of those ideas comes from serious, credentialed physicists working through the honest mathematical consequences of theories that are otherwise well-tested and broadly accepted. What none of them offer, not one, not even a little, is any known mechanism by which a civilization living inside one universe could reach across into another and actually draw usable energy back. If other universes exist in any of these senses, they appear to be sealed off from one another in the most complete way physics can currently describe. Not merely distant, the way another galaxy is distant, but structurally, mathematically separate, with no known door between them. That's worth sitting with plainly, because it marks a genuine shift in the nature of this entire conversation. Every rung we've climbed until now has stayed inside the boundary of testable physics. Even when the engineering was purely theoretical, a Dyson swarm has never been built, but the physics describing exactly how one would behave and exactly what signature it would leave is solid, checkable, real. A civilization reaching across into another universe entirely doesn't have that foundation underneath it. It's the point where this exploration stops being disciplined extrapolation from known physics and becomes something closer to pure philosophy wearing the vocabulary of physics. Worth naming honestly, rather than blurring the line the way a less careful video might. There is one place even here where the honest physicists keep at least 1 foot on solid ground. If crossing between universes were ever possible in any form, it would almost certainly require something like a traversable wormhole, a bridge through space-time connecting 2 distant points or 2 distant realities, held open against its own overwhelming tendency to collapse. General relativity, our best working theory of gravity, does technically allow such bridges to exist as valid mathematical solutions to its equations. But keeping one open appears to require a form of exotic matter with genuinely negative energy density, and the only negative energy effect we've ever actually measured in a laboratory, a subtle quantum phenomenon called the Casimir effect, produces an amount so vanishingly small that it would take resources far beyond anything even a fully realized galaxy-harvesting civilization could gather to matter. The door, if it exists at all, appears to be locked from a side nobody currently knows how to reach. Now let's push past the multiverse entirely, into an idea that a working Oxford philosopher published, and that professional physicists still argue about today. Here's a sentence I want you to actually consider seriously, not as a spooky hook, but as a real argument that a working Oxford philosopher published in a peer-reviewed journal, and that professional physicists still argue about today, 20 plus years later, without having found a clean way to dismiss it. Statistically speaking, it is more likely that your mind, right now, reading these words, is a simulation, than that it's the original. I know how that sentence sounds. Stay with me, because the reasoning behind it isn't mysticism, and it isn't a plot device. It's a counting argument, and counting arguments are some of the hardest things in mathematics to actually escape once you accept the starting premises. Here's how it works. Suppose that somewhere far up this ladder we've been climbing tonight, a civilization eventually becomes powerful enough to run extremely detailed simulations of entire worlds. Complete histories, complete populations, complete conscious minds inside them, none of whom know they're inside a simulation. Because from the inside, a sufficiently detailed simulation is simply indistinguishable from reality. Now suppose that civilization, or civilizations like it, don't run just one such simulation. They run many. Ancestor simulations, historical recreations, entire branching worlds, the way we might run a video game except populated by minds that genuinely think and feel and wonder about their own place in the universe, exactly the way you're doing right now. Do the arithmetic, and something uncomfortable falls out the other end. If even a modest fraction of sufficiently advanced civilizations choose to run even a modest number of these simulations, the total population of simulated conscious minds across all of them would vastly outnumber the population of minds living in the one original unsimulated reality at the top of the stack. Possibly by billions to one. And if that's true, then a mind selected at random from that entire pool is overwhelmingly more likely to be one of the simulated many than one of the real few. The philosopher Nick Bostrom formalized this argument in 2003, and it's held up remarkably well against 2 decades of serious, sustained attempts by very smart people to knock it down. Here's the part that almost always gets lost when people repeat this argument secondhand, and it matters enormously. Bostrom never actually claimed that we are, in fact, living inside a simulation. What his argument actually proves is narrower and, honestly, stranger. It proves that at least one of 3 statements has to be true, and we currently have no reliable way to determine which one it is. Docker number 1. Almost every civilization capable of reaching that level of power destroys itself, or collapses, or simply never gets there for some other reason, meaning the simulators never come to exist in the first place, and the whole scenario never gets off the ground. Door number 2. Civilizations do reach that level of power, routinely, but for reasons of their own, ethics, disinterest, restrictions we can't currently guess at, they almost never actually choose to run these kinds of detailed simulations. Door number 3, they do exist, they do run them in large numbers, and we are, right now, almost certainly living inside one. One of those 3 doors has to be standing open. We don't currently have any tool, any experiment, any piece of evidence that tells us which one. And here's the detail that makes this genuinely unresolvable, rather than just uncomfortable. Any experiment you could possibly design to test whether you're in a simulation would itself be running inside that same simulation, and would therefore return whatever result the simulation was built to give you. There is, as far as anyone has figured out, no lever inside a sufficiently well-built simulated reality that reaches the outside of it. That's not a temporary gap in our technology waiting to be closed by a smarter instrument next decade. If the scenario is real, it may be a permanent structural feature of the situation forever. Which door do you think is actually standing open? Not which one is the scariest to say out loud. Which one do you actually think is true? And why? I want real arguments in the comments on this one, because this is the single most debated idea in this entire video among the people who study it professionally, and I think the disagreement itself is more interesting than any one answer. I want to be careful here, because it would be easy to let this spiral into something it isn't. This argument is real, published, and taken seriously by working physicists and philosophers. But it is also a counting argument built entirely on the assumption that civilizations at a certain level of power can and do exist, which is exactly the open question this entire video has been circling from a dozen different angles. It doesn't prove anything about your actual life. And here's the calm center that I think genuinely matters more than the vertigo. If the world around you is detailed enough to contain everything you have ever loved, everyone you have ever cared about, every sunrise that's ever felt real to you, then it is detailed enough for those things to matter completely, regardless of what they're ultimately built out of underneath. The question of the substrate doesn't reach down and touch the actual living of a life. You can hold this entire argument in your head, follow it all the way to its genuinely unresolvable end, and then set it down and go make dinner, and the dinner tastes exactly the same either way. There's an old line from the science fiction writer Arthur C. Clarke that fits this moment almost too well. Any sufficiently advanced technology is indistinguishable from magic. Push that line one step further, and it sharpens into something a little more unsettling. Any sufficiently advanced civilization becomes, for all practical purposes, indistinguishable from a god, not as a metaphor, but as a literal description of capability. A civilization that can create fully detailed worlds, populate them with conscious minds, and shape their entire histories at will is doing, in concrete and physical terms, exactly what every human religious tradition has ever attributed to a creator. That's not me forcing a connection where none exists. It's what falls directly out of the physics and the mathematics themselves once you follow the reasoning honestly, without flinching away from where it actually leads. And it's worth sitting with the fact that a scale built by a Soviet radio astronomer in 1964 to solve a completely unglamorous engineering problem, how strong would an alien radio signal need to be for us to detect it? Ends up, 60 years later, walking straight into one of the oldest questions human beings have ever asked themselves, in the dark. Let's climb the last real step before we reach the actual summit, because there's a serious, published, physically grounded idea sitting right below the top of this ladder that almost never gets talked about, and it deserves the same careful treatment we've given everything else tonight. The physicist Frank Tipler, in a 1994 book, proposed what he called the omega point, a theoretical far-future state in which a sufficiently advanced civilization gains total control over an entire collapsing universe in its final moments, harnessing the crushing energy of that collapse to perform, in his framework, an effectively unlimited amount of computation compressed into a finite span of time. In Tipler's original vision, that unlimited computation would be powerful enough to reconstruct, in complete and total detail, every mind that had ever existed across the entire history of that universe. A kind of physical resurrection, arrived at not through faith, but through pure physics, pushed to its absolute theoretical limit. I want to be honest with you about where this idea actually stands today, because the honesty matters more than the drama. Most working physicists do not accept Tipler's specific cosmology. His version of the omega point depended on a universe that eventually stops expanding and collapses back in on itself. A big crunch, which would have supplied the enormous final burst of energy his framework required. But every measurement we've been able to make points the other way entirely. Our universe isn't slowing toward a collapse, it's accelerating outward, driven by the same dark energy we already talked about, heading not toward a fiery crunch, but towards something much colder, slower, and quieter. An endless dilution rather than a dramatic ending. The specific engine Tipler described appears to have no fuel available in the actual universe we live in. So we treat his idea honestly. A serious, genuinely creative, ultimately rejected attempt to describe what the very top of this entire ladder might look like. What survives from it, even after most of the specific physics has been set aside, is the shape of the question itself, and that question is worth keeping. Is there a final state a sufficiently advanced civilization could, in principle, ever reach? Does the universe permit an actual ending that's something other than simply cold, empty, and finished? Or is a slow fade into nothing the only ending physics is willing to offer? No matter how much power anyone manages to accumulate along the way, there's a gentler and, to a lot of people, a far more beautiful attempt to answer that same question, and it comes from a name you already know from earlier in this video. The same Freeman Dyson who first taught us to hunt for waste heat around individual stars. In 1979, Dyson wrote a paper called Time Without End, asking whether intelligence could survive forever in a universe that keeps expanding and cooling forever, rather than one that eventually collapses back in on itself. His answer was a cautious, carefully qualified yes, and the mechanism he proposed is genuinely lovely. As the universe grows colder and usable energy grows scarcer and scarcer over unimaginable stretches of time, a sufficiently advanced civilization could survive indefinitely simply by thinking more slowly, spacing its thoughts out across ever longer intervals, conserving its dwindling energy budget by patiently stretching it across more and more time, rather than trying to outrun the cold. In Dyson's picture, a mind need never actually die from the universe running out of usable energy, because it could always thin its thinking out to match whatever the universe still has left to offer, forever, no matter how little that eventually becomes. Notice that Tipler and Dyson were, in a real sense, reaching for exactly the same rung from two completely opposite directions. Tipler imagined a civilization cramming infinite computation into the fiery, violent instant of a universe collapsing in on itself. Dyson imagined a civilization thinning its own thought out gently across an endless, expanding, cooling dark. Both were asking the same underlying question. Can intelligence, in some form, actually become permanent? And both ran headlong into the same modern complication we already met earlier tonight: the accelerating expansion of space. Dyson's slow, eternal thinker assumed a universe that would keep offering up small, usable differences in energy to think with, gaps and gradients a patient mind could exploit forever. An accelerating universe may not oblige, because it appears to be heading toward a state of uniform, featureless cold, in which no meaningful difference in energy remains anywhere for any kind of thought, however slow, however patient, to find a foothold in. Which means both of the serious, honest, physically grounded attempts to describe the actual ceiling of this ladder sit under the exact same shadow. The same dark energy that seems to want this particular universe to end not in fire and not in eternal thought either, but in a quiet, even thoughtless chill that no amount of cleverness gets around. That might be the single most sobering fact in this entire climb. The universe we actually happen to live in appears to be built, structurally, in a way that quietly forbids its own ceiling. It lets us imagine the very top of this ladder with perfect clarity, and then, gently, without any drama at all, declines to provide the fuel for anyone to actually reach it. There's one more real idea worth including before we close the loop on all of this, because it's the point where the far future of a civilization and the near future of an individual mind start to blur into the same question, and it's grounded in genuine, ongoing physics rather than speculation alone. A piece of music isn't the vinyl record it's pressed into, or the radio wave carrying it, or the speaker vibrating to reproduce it. It's a pattern, one that can move between completely different physical materials and still remain recognizably itself. A growing number of serious researchers in both neuroscience and physics take seriously the idea that a mind might work the same way. Not identical to the specific neurons it happens to be running on right now, but a pattern of information and process that could, in principle, be read, copied, and run on an entirely different substrate. a sufficiently advanced computer for instance, while remaining, in every functional sense, the same mind. Nobody has actually done this. It remains, as of right now, firmly in the category of serious theoretical possibility rather than demonstrated fact. And there are real, unresolved scientific arguments about whether it's even possible in principle, let alone practice. Questions about whether consciousness itself is the kind of thing that can be fully captured by a pattern of information at all, or whether something essential would be lost in translation between one substrate and another. But the idea connects directly back to something we already discussed earlier tonight, when we talked about Barrow's inward-turning civilizations and the Matrioshka brain. A mind the size of a solar system, built by pointing an entire Dyson swarm's worth of energy at pure computation instead of expansion. If minds really are, at some fundamental level, patterns rather than specific arrangements of specific matter, then a civilization advanced enough to master that transition wouldn't just be building bigger and bigger machines to think with. It would be quietly redefining what it even means for its own citizens to be alive, moving from bodies that age and fail and eventually stop, towards something closer to a pattern that persists as long as something, anything, keeps running it. That's an enormous, almost unimaginable shift, and it's worth being honest that we genuinely do not know whether it's physically achievable, whether it would actually preserve whatever it is that makes a mind feel like itself from the inside, or whether it's simply a beautiful idea that runs into a wall we haven't discovered yet. But it's not idle fantasy either. It follows directly from serious, ongoing questions in real physics and real neuroscience about what information actually is, and whether it can, in any meaningful sense, outlive the specific physical thing that first gave rise to it. It's also, worth noting, one of the only ideas on this entire ladder that connects the enormous, cosmic scale of everything else we've covered tonight back to something genuinely, immediately personal. Every other rung describes something a civilization might do, out there, far away, over spans of time too large to feel. This one describes something that would happen to you, specifically, individually, if it ever became real in your own lifetime or the lifetime of anyone you know. Which is probably why, out of every idea in this entire video, it's the one people tend to argue about the most fiercely and the most personally in the comments of videos like this one. So here's where all of this actually leaves us, and I want to bring it all the way back down to ground level before we close, because I don't think the real subject tonight was ever really the aliens at all. We are a species sitting at 0.73 on a scale that runs, as best anyone can currently tell, from a planet that hasn't yet learned to use its own sunlight, all the way up to something that starts to look, the higher you climb, uncomfortably close to godhood, not through mysticism, but through the plain, patient, physical accumulation of energy and control, one honest, checkable rung at a time. We have not yet finished mastering the light of our own star. We have looked, with real instruments and real mathematical predictions rather than guesswork, across 100,000 entire galaxies for the one signature that no civilization, anywhere, at any level of advancement, should be able to hide from the laws of thermodynamics. And the sky came back dark. Every single time, in every single search we've ever actually run. We checked nearby stars for the telltale nudge of a stellar engine, and found none. We checked the solar system around us for any sign of a self-replicating probe quietly going about its business among the asteroids, and found nothing. We circled one 72-second anomaly in red ink in 1977, and never saw it again. We don't know if that combined silence means we're early. The very first arrivals at a party the rest of the universe hasn't gotten to yet. We don't know if it means we're rare, one of a small handful of species anywhere that ever made it this far up the ladder at all. We don't know if it means the most advanced minds in the universe have simply gotten too quiet, too small, too inward-turned, too busy thinking rather than building, for anything we currently know how to look for to ever notice them. Every one of those explanations is still, tonight, genuinely on the table, held seriously by genuinely credentialed people, and any single one of them could turn out to be the real answer once we finally have enough data to know for sure. And underneath every rung of the ladder we climb tonight, from a planet, to a star, to a galaxy, to the edge of the observable universe, past the edge of testable physics entirely, and into the strange, undecidable territory of simulated minds and civilizations that have stopped needing bodies at all, sits the exact same original question a working Soviet radio astronomer sat down with in 1964, trying to solve an unglamorous, practical problem about how strong a signal would need to be for us to ever catch it. He almost certainly had no idea that his 3 modest steps would end up carried this far by dozens of other serious scientists across 60 years into territory that stops sounding like astrophysics somewhere around the 8th rung and starts sounding like the oldest questions human beings have ever asked themselves, alone in the dark. How much can a mind actually become, given enough time, enough energy, and enough will to keep climbing? And is anyone else out there already climbing it right now, somewhere above us? Leaving no trace we currently know how to see, we genuinely don't know. I'd rather leave you with that plainly than dress it up into something tidier than it actually is. But you now know exactly how the real search actually works. What real evidence would actually look like if it ever showed up. And why the silence itself is a piece of that evidence, not simply the absence of any. Before you go, I want you to actually answer something, because I think the disagreement here is more interesting than any single answer could be. Which door from Bostrom's argument feels most likely to you, and why? Whether you think the silence across 100,000 galaxies means we're early, or rare, or simply built the wrong instrument to notice what's already there. Whether you'd rather live as a Type 1 civilization that finally learned to use its own planet gently, or skip straight past every rung on this ladder to whatever's waiting at the top. Say it plainly, with your actual reasoning, not just a single word, because I read every one of these, and the best conversation under a video like this one has never once been the agreements. It's always been the arguments. We are a 0.73 civilization, standing at the very bottom of a ladder that may not have a top at all, looking up. That's not a small thing to have thought through carefully, together, in the dark.